When I was a little girl, I was fascinated by the legend of El Popocatépetl. I always wondered what it will be like to look into the volcano's mouth and see solid rock turn into boiling hot liquid lava. Now I know that, in chemistry terms, all we're really looking at is a phase transition, the shift from one physical state to another. Our job today is to make sense of them. Esto es Real Chem. Chemistry can help us make sense of the world around us. When thinking about how and why lava forms, phase diagrams can be a roadmap to understanding the conditions under which different phases of a substance exist. Exploremos. Phases are homogeneous substances with uniform physical and chemical properties. What do chemists mean when they say homogeneous and uniform, though? Let's make sense of this by using a concrete example. Ice is an example of a phase. It is made of pure H2O and it is a solid. Water is also a phase. It is also pure H2O and is a liquid. But when you put crackling ice on your favorite drink, you will have different phases. Water and ice are chemically identical, but they are physically different. Another example is ice and dry ice, which is solid CO2. Dry ice is often used to create a creepy, smoky effect on haunted houses. Ice is water, and dry ice is carbon dioxide. A substance's phase diagram shows the temperatures and pressures at which a given phase is stable. Stable in this case means the properties and the composition does not change. For example, the phase diagram for water shows that ice is stable at temperatures below 0 degrees at normal atmospheric pressures, but melts to become water the moment the temperature raises even a tiniest bit above that. This is called the melting point. Liquid water becomes unstable above 100 degrees and converts to water vapor, a gas. That is called the boiling point. This means you have observed in your everyday life how a substance changes phases. A substance's melting point and boiling point change with pressure. This can be seen when we examine the curves of the water phase diagram. For example, the red curve is the liquid vapor curve, or phase boundary. It tells you the temperature at which water boils and becomes water vapor, or water vapor condenses into water. It has a positive slope, reflecting that higher temperatures are required for boiling as the pressure increases, and lower temperatures are required at lower pressures. On top of Mount Everest, the ambient Earth's pressure is much lower, so you only need to reach 71 degrees to boil water for a cup of tea. The point of intersection of all these three curves are called the triple point. It is the pressure and temperature at which these three phases of water coexist in equilibrium. Another important point on the phase diagram is the critical point. At temperatures and pressures above this point, water forms a phase of matter known as supercritical fluid. In this region, distinct liquid and gas phases do not exist, and the supercritical fluid has properties that are intermediate between those of the gas and the liquid. Different substances have different melting points and boiling points, and therefore different phase diagrams. In simple terms, the nature of the intermolecular forces, that is, the relationship between the molecules, will determine the shape of the phase diagram. So a volcano is simply one window into phase transition. Temperature and pressure changes on rock cause solid rock to become molten lava, similar to the changes we saw on the H2O phase diagram. Chemistry always makes sense, and now you have the tools to make sense of it. No matter whether you're looking at water boiling while you cook or observing the Popocatépetl looking after Iztaccíhuatl, remember, you engage with chemistry everywhere you go. Explora y diviértete. So explore and remember to have fun.